In the previous segment, we discussed about the systems where multiple bodies were connected through different connectors, and we saw how to deal with those specific connections, so that when we remove each of those bodies to draw their FBDs, we will use those connectors property to write the forces of interaction between the bodies. So that was the major idea, and once you understand that major idea, the problem should be fairly simple to then analyze, because everything boils down to just splitting the whole system into various single body systems, and we know how to write equations for the single body systems, and then it's done. Now today in this present segment, what we are going to discuss is, as promised, about a system where a very large number of bodies are connected, maybe in hundreds, and that specifically we will call as a the case of trusses. Basically we are going to deal with, but we are studying as a concept, we are studying this under the heading that large number of connected bodies. Otherwise basically it's about trusses. But before we actually get into the trusses and the spatial techniques which are used to solve the truss problems, or to analyze the truss, I should say, in general, I'll just go through one or two concepts which will be beneficial in understanding, defining and analyzing trusses, and those are something called 2 force members and 3 force members. Okay. Now what are 2 force members? Now suppose we have a body, and then if we know that there are 2 forces acting on the body, F1 and say F2, and if we also know that this body is under equilibrium, it is in balance under the action of these 2 forces. Okay. So first of all, why this body is called a 2 force member? Because this member or the body is subjected to only 2 forces. But then if we know that this body is in equilibrium, then there is a definite relationship between these two, that is, they must be collinear and exactly opposite in their sense. That means if this body is in equilibrium, then this cannot be the situation. Actually the situation should be in a way, for example, this force should have been in this direction maybe. Okay. So F2 dash, if I say, so it should have been in this direction for the body to be in complete equilibrium. Otherwise what will happen is, maximum this force will have a component which will balance this, but there will be a other component in the vertical direction maybe, or perpendicular to this, which will not be balanced by this force, and the body will not be in equilibrium. So for everything to cancel out 2 forces, if they are acting and if the body is in equilibrium, they must be collinear. Either this or maybe the other side also I could have drawn. For example, that could also be a case where the body will be in equilibrium. Okay. So like that. So I could have said that F1 bar prime maybe. So that also could have been a situation where the body will be in equilibrium. Okay. But not in F1, F2. When there is an angle, there is some angle between them. Okay. So that's the condition of 2 force members. And then the next point which I wanted to make was about 3 force members. Okay. So say 3 force members. Now what are 3 force members? As the name suggests, obviously the body will be subjected to 3 forces. So suppose this is the body, and the body we have some 3 forces, and like that, F1, say F2 and F3. But now if we know that this body or this member is in equilibrium under the action of these 3 forces, then there are 2 conditions must be satisfied. That is, say A, they must be concurrent. Okay, that means if you join them tip to tip, if all the tips are connected, so they must pass through the same point, a single point. If you join them, okay, say tip to tip, tip to, sorry, tip, if you join, so they will pass through a single point. But now if the other condition is if so they should balance, they should be in sorry, they should be in balance. Okay, that means if you join them tail to tip, tail to tip, then what happens is they must form a triangle, be formed. Okay, a closed triangle, actually there should not be any open end. Okay, that means if this body is in equilibrium under the action of these 3 forces, and then if I extend these line of actions, so what should happen is and say like that, my forces should always, so see here, and if I, so this is the point through which all the 3 forces, they are passing through this point. Okay, this point. So so that is the first point, that is tip to tip. If you join them, because the forces are transmissible, and you just pull them apart on their line of action, you are not free to move the line of actions as such. So if you move them along the line of action and bring the tips to come together as far as possible, and then you should have a point where everything meet, all the 3 forces meet. And if you put them like this, tail to tip, say, so if I call this F1, this is F2, and say this is F3. So I have drawn now say F3 here, and say okay, I'll draw say F2, sorry, F1 here, which is parallel to that, and now the length of F2 must be such that if I draw here, it should just end at the tail of the vector F3. Okay, so that triangle is this point, tail to tip. If you join all the 3 vectors, it should form a closed triangle. So that's the condition that a 3 force body or a member will be in equilibrium. Okay, so these 2 concepts are really very important for any system to be in equilibrium in general, but then once we come to analyzing your the systems of trusses, these concepts, mainly the two force member concept, will be very, very important. So we will see how these concepts will be used, and then analyze the trusses in future in the next segment. See you then.